So let's get started with going over the Voltaic cell concept skills worksheet. This is a combination of all the skills we've done so far, and I hope that you see this in a new light with all the things we've been doing. So let's get started. So I want you to basically fill this diagram that's incomplete for a Voltaic cell, and the materials that are listed are very important, and they spell out some things. I have tin, copper, tin nitrate. In fact, this is going to be tin Roman numeral 2, so we say tin 2 nitrate. What do I know? Because nitrate's -1, and for this compound to be what? Neutral, tin has to be what? +2. So it's very important to realize that the salts that they give me right here, what ions I'm dealing with. So you'll see me do this, so let's write this. So you should be able to see that tin 2 nitrate, because, well, we're going to find out why, is going to break apart into tin +2. And if you notice, this little 2 means 2 nitrates. NO3, -1, I'll put our 2 in front. You notice we're +2, each nitrate's -1, but we have 2 of them. So it's -2 and a +2. The overall compound is electrically neutral. And we now know that the ion that dissociates when we have this salt in solution, and I really should have put aqueous to let you know. This is a solid aqueous. I really should put aqueous here, now that I think about it. Hey, too bad. All right, for you, I guess. All right, any case, so we know we have tin +2 in that reaction. And the other one, copper nitrate. Now, very careful. We've been dealing with a different charge of copper in our other problems. So this one, copper nitrate, notice there's 1 copper. So copper, this would be copper 1 nitrate, only because I can tell that it's going to be, and I should not have put the parentheses. It was not necessary, although if I leave it there, it wouldn't be wrong, but CNO3. Okay, so because it's Cu, which is plus something, and nitrate we should know is -1 as this cluster polyatomic ion, should make sense to you that this is going to break apart and dissociate into copper +1, or just copper plus, and 1 nitrate, NO3-, has to be. So by giving you these compounds, and again, I should have said aqueous, I feel bad, now I'm over it, it really means that in solution, okay, I've got tin +2. By the way, this is the element symbol for tin is SN because of stannum. That's a Latin name for tin. And cuprum, okay, is the Latin name for copper. Those are the 2 ions. Now, it's important that we realize the only way that this really works, if these compounds are soluble. So the idea here is that if these guys are soluble, so we should know something. Nitrates in our solubility rules are always going to be soluble because nitrates have a low charge. They're -1 stretched out over 4 atoms. So the Coulombic attractions are weak. So anytime you've got nitrates in a compound, they'll always dissociate. Okay, now that we know what the ions are in solution, okay, what we have is we have our tin and we have our copper. And what I'm going to do now, knowing that I'm dealing, okay, with tin +2 and copper plus, I'm going to go to the reduction potential because I know my half cells, okay, are going to be basically the metal and the corresponding ion that goes with the metal. That's how we have built these reduction potentials based on the standard cell experiment that I've talked about previously. Any case, all right, so when I look at copper 1, and remember, we go to reduction potentials. This I rewrote from you, and I just kind of transposed this from the table. We go to our standard reduction potential tables, and I find copper +1. So I had to know that copper +1, okay, came from the basically from this salt that dissociates. Okay, so let me get my color that I want. So this copper +1, it was key for this problem to realize, came from this dissociation. And of course, when it reduces and gains an electron, GER, G-E-R, gaining electrons is reduction, it becomes pure copper solid. and that's my reduction potential right off standard table. And the same reasoning how I figure out Sn plus 2 for the same reason. It's soluble. Okay, so I've got basically my tin hooking up with tin plus 2, and I've got my copper, okay, with copper plus 2. And that's basically how the cells are going to work. The question is, which metal electrode is my anode? Is it the tin or is it the copper? Okay, so what we do is we go to the reduction potentials, and because they're written as reduction, the value or the measure of the ability to oxidize is going to be the reverse sign. So if you notice, of the two half reactions I have here, the reduction potentials of the ions, the ion that's the worst at reducing must mean it's really not, it's not spontaneous in the forward, which means it's spontaneous in the reverse. So the ion that's the worst at reducing means that the reverse sign, SN0, is going to be the greatest at oxidizing. So the most reactive, okay, the most reactive metal that we have of the two, based on what I'm doing here, is the tin plus 2. Okay, so the tin. So this is the most reactive metal. If you don't understand that, anytime we deal with oxidation, remember our table of reduction potentials, just by convention, is written all as reductions. So this is a measure of reduction. As we learn positive volts, to get oxidation, I reverse. So when I reverse the signs, this is a greater positive. This will become a negative 0.52 for copper oxidizing, and we learn copper hates to oxidize. That's why it's more expensive. And tin, when it goes in the reverse, is positive 0.4. So clearly the more spontaneous metal, the better pathway for metal oxidizing is tin. And therefore, I have just found the one that's the best at oxidizing is tin, and this is my anode. Okay, how do I know? Because of the mnemonic that always works for all of our different electrochemical cells. And what we learn, anox, red cat, which means the anode is always the place of oxidation. So where do I put this? Because both sides could be the anode. Well, the key here is that in the first instructions it said what? Please complete the diagram so the current flows from left to right. So if the current is going to flow from left to right, we know that the anode must be on the left. And you say, well, how do I know that? Well, electrons, or the current, are always going to flow from the anode to the cathode. Why? Well, the anode is where oxidation occurs, and oxidation is the place where electrons are released or lost, Leo, okay? And of course, the cathode must be to the right. So electrons flow from the anode, the place that loses electrons, oxidize the place that accepts them, always. So by saying left to right flow, I know the anode is here. And what does it also tell me? Well, we know the anode from the standard reduction potentials has to be tin. And therefore the cathode must be the copper. Okay, so that's how I did that. All right, now they want you to write the ions. Well, as I said before, we always put the metal with the associated ions here. So we want tin, and we need tin plus 2. So in this solution, we're going to have tin plus 2. And you say, Mr. Grodsky, isn't it really tin nitrate? Yeah, but the nitrates don't do anything. They kind of spectate. Their charges aren't great enough. Okay, so it's going to spectate in this example. All right, so we have that. So over here we have copper nitrate over here, but that really means we have free copper plus 2. And in truth, we do have the nitrate ions, so I really should write them. They ask for all of them. So this should be NO3 minus. Okay, now they also want you to put the correct molarity of the solutions at standard constant conditions. So these reduction potentials they measured from the standard experiment, okay, was done so at standard conditions. Those standard conditions are 1 atmosphere of pressure, 298 Kelvin or 25 degrees Celsius, and 1 molar concentrations. I'll go 1.0 molar. So these concentrations are 1.0 molar. 1 mole of copper ions per liter of solution. Molar of what? Well, we could write Sn plus 2, or we can write Sn, okay, NO3. And of course, and this is 1.0 copper nitrate. Now I can see I made a mistake already and people are yelling at me. Okay, but I catch my mistakes. This should be +1 ion. Again, we're so used to using the +2. I am not free from error. Okay, so there we go. And I believe we have one more piece. We want to illustrate the flow of current and the movement of both the cation and the anion. Fancy words, cation is the positive ion and the anion is negative. So if the salt is KCl. So KCl is soluble. How do I know? Because K is +1. All group 1 ions, alkali metals, are +1. Halogens, Cl negatives, or -1. They have a weak attractive force. So in water, they make K+ aqueous and Cl negative. So these are our 2 ions. And very simply, how would they go? Well, we know the anode, a little piece of it, is going to disappear as a solid and make tin +2. So to basically counterbalance the increase of tin +2, the negative ion of the salt that dissociated is going to move down. And over here, we're going to lose copper +2 when it becomes pure copper and it reduces. And we're going to lose the +1 copper. So the K+ that's already in the salt bridge is going to migrate down to counterbalance. Okay? And of course, there are also some other movements of ions that make sense as well. Okay? So that's the diagram. And so let's write our oxidation half reaction, which we can get. Okay, we learned that the tin is going to oxidize. It's going to be in the opposite direction. So we're going to have tin 0. Let's do that in different color. So tin 0 oxidizes. We're going in the reverse direction. If it's non-spontaneous in the forward, it's definitely spontaneous in the reverse. So tin 0, okay, is going to lose 2 electrons and become tin +2. We show the 2 electrons in our half reaction so that both sides of a half reaction have the same charge. +2, -2, 0. Let's write the sign in for the voltage. It's not negative. Now it's positive 0.14 because now we're talking about the reverse. Okay, the reverse is spontaneous. And what's nice about voltage, which tells us we have the energy, okay, to push the current around. Now, what's being reduced? Well, as written, copper +1 is going to get reduced. So copper +1, and the idea it's reduced is charge goes down. Copper +1 gains an electron and becomes copper 0. And when it does so, okay, as we see from our net potential table that I transposed for you, as written, it's 0.52. So 0.52 volts. Okay, now these aren't really the correct half reactions. Okay, and you may say, well, why, Mr. Gradsky? Well, even though both sides of a half reaction individually have the same charge, the electrons are not balanced. Okay, you can see that there are 2 electrons being given off, and there's 1 being accepted in this redox reaction. So therefore, we're losing an electron in this process. It can't happen. Or we're gaining an electron, that's how we want to think about it. So we have to balance the charge. So what we do, party people, is we multiply by the distributive property to do so. So because this has 2 electrons, this has 1, we have to make sure the same electrons being what? Accepted or pulled or get reduced by this compound is the same as being released. So we have to balance the electrons first. So the best way to get the same number is when I multiply everything by 2. Why? Well, by distributing 2 and timesing everything by 2, this becomes 2 electrons, 2 coppers. If I multiply everything by 2 on both sides of an equation, nothing changes. Why? Well, +2, -2 gives me a 0, and this is a 0, so I'm able to do that. But the biggest reason, again, why I do that, now I can cancel out my 2 electrons. And when you balance the electrons, you automatically balance the charge of the half reactions with each other, the oxidation and the reduction, and you automatically balance the overall net ion. When I say net, I mean I'm just using the ions involved. Notice nitrate really isn't involved, so it's not part of it. So now I just put these together. Tin 0 is on one side, so SN0, plus copper +1. I don't put the electrons in because they're canceled. And then I have tin +2. Nice place to go in the summer, tin +2. Or tin +2. 2. Okay, and then I have, plus copper 0. Now I can check to see if I am right by looking at the overall charge. Now, I'm going too fast here. I have to make sure I put the right coefficients, because there was 1 tin, but there's 2 copper plus 1s, and there's 1 tin plus 2, but 2 copper. So I'm going too fast for myself. Make sure you maintain the same coefficients, as I almost did not. Bad Grodsky. Okay, now, once we've done that, now we're going to check for the overall charge. Well, tin is 0, even though I'm writing it here. An element by itself with no charge is 0, standalone. Okay, but 2 times plus 1 is plus 2 overall. And 2 times 0, 0 in this side, because you have 1 tin plus 2, and individually it's plus 2, the whole thing is plus 2. So you can see the charge on the reactant side of my overall net ion reaction is the same as the product side. Okay? And then let's do the net potential, the overall E0 of cell. And we can just add this together to get these two together. Careful of your signs, they're both positive. So we get 0.66. Okay? All right. And we can put that right into the digital voltmeter. All right? So much fun. And it's a positive 0.66 volts. Spontaneous in that direction. Moving forward, let's go to, or actually going downward, are we? Any case, let's go to K. Okay? All right, you got it. Would the voltage increase, decrease, remain unchanged if the salt bridge compound was changed to K2S? Let's think about this. K2S. Is it soluble? That's my first question. Does it have a group 1 ion? Yes, and this is because it's plus 1. Is a weak attractive force, so all group 1 ions, because of their low Coulombic attractions, right, they're big ions with a low charge, will not attract the other negative ion that strongly, and water can get in and break them in. So this is going to break apart into 2 K pluses in water. So this solid becomes 2 K pluses. Aqueous means dissolved in water, plus an S negative 2 aqueous. So it's soluble, so this occurs. So what I'm adding is K plus. Let's go back and see what happens. Now if I added, all right, K plus and S negative. Well, I think I have an issue with this, because K plus, okay, is a common ion with the salt bridge, but is it a common ion in the overall reaction? Does the overall reaction have any K's in it? And the answer is no. So the extra K plus is good for us. We have more of them to come down to counterbalance the loss of positive as the Cu plus 1 reduces, but that has absolutely no effect. What about the S negative 2? The S negative 2, my friends, in chemistry, is a very attractive ion. Now, it couldn't get it done with K plus because it's plus 1. It had remember, this is a big ion that's plus 1, so the attractive force was weak. But the S negative, okay, now S negative 2 would run down to this side, and look what's down here. A positive 2 ion. What did we learn? Things that are what? Insoluble are mainly because the charges are high. So what we'd have in this issue when it runs down, the S negative 2 aqueous free ion would react with the zinc plus 2 that's given off when the zinc what? I'm sorry, zinc. I'm thinking of another problem. When the SN, when the tin becomes tin plus 2. So these guys would attract each other strongly to make something we call a precipitate. Now, even though I wrote it this way, the metal always goes first, so the tin plus 2 and the sulfur is negative 2, and we would make a solid. So this being aqueous, that was in the salt bridge, this being aqueous. So we would make something called a precipitate. A precipitate means the ions stick together and a solid would appear. So what would happen, party people and people that want to go to the party, you would start seeing cloudy buildup of precipitates until you couldn't see this anymore. But that's not what I'm after. Wouldn't the S negative 2 with its high coulombic attraction attract the Sn plus 2 so strongly and make it into a what? Crystal? If that's the case, it's going to take away the Sn plus 2. This idea of precipitating out this ion out by becoming a solid and taking it out of solution means that we are doing what? Decreasing Sn plus 2 concentration. Notice I write the brackets to show that molarity is going down. We're taking the Sn plus 2 out of the solution because the S negative 2 that came from this soluble salt is highly attracted, and we make what we call a precipitate. So, what do we know? Well, I'm going to write over my work here. Okay, let's make it, I don't know, orange. So I am going to decrease Sn plus 2. Let's get the orange. What do we have? We have our stress. We have our response. The Chatelier's problem. We're going to lower the Sn plus 2 ion, so the response is going to want to increase the Sn plus 2. Okay, how do I increase the Sn2? Remember, the reaction is now going to be more spontaneous in the direction that makes more Sn plus 2. So what is going to be that shift? That shift is going to be where? Well, to make more Sn2, it shifts to the right. Right? Shifts to the right. So as we said in class, we know that we have this little chart here. Here's my equilibrium. This is Sn plus 2 is a product, and if I was to lower the concentration of Sn plus 2, remember this is 100% Sn plus 2, all right? If I'm I'm going to start here because I am currently spontaneous, because I do have positive volts, so I am moving down in this direction to the right now. But if I'm going to lower my Sn plus 2 solute, that's what we do, okay? So if we lower, it's going to basically shift. So by lowering the Sn plus 2, as we talked about in class, we're going to push this boulder more up the hill. So I'm going to push it up. I'm putting more energy in by doing this, right? If this is 100%, I'm going to go this way. So I'm putting this position now what? Higher. Oops. So it's going to be higher. And now we're more spontaneous. Bottom line is it shifts to the right. You know the Ford reaction is more spontaneous, and the voltage has to increase. Okay, let's go on to the second question. All right, so this is really the same kind of problem. So we had some practice, so we're going to move a little faster. What I did do is draw the reduction potentials. The key for me, again, is looking at the salts. I should have wrote aqueous here. So these are the salts. These are soluble because of nitrates. There's 3 of them. Each nitrate is what? -1. So chromium has to be +3. So that's how I know I'm dealing with chromium +3 as my ion. And of course over here I have iron nitrate. That dissociates into iron +2 because each nitrate's -1. And we know nitrate's always soluble when you have a nitrate, just because you're stretching out -1 over 3 atoms. And because it's overall -2, iron is +2. Okay, so that's something we should be able to handle from the first page. Knowing that, and knowing I'm dealing with chromium +3 in one cell, and pure iron metal, and iron plus, in this case, 2 in another cell, those are the cells that set up. Now in the directions, I'm saying I'm going right to left. The current flows from right to left, and the source of all the electrons is always the anode. So that screamed and told me the anode here, and now the cathode is right here. Now who is the anode? Well, I do not have these metals at a table. I sort of do with a reduction table, but I want to know what it reduces into, or what it oxidizes into or reduces into. So I found my metals on the reduction table, but I had to know what ions are involved, okay? And putting this in the beaker with it told me what ion metal combination. So looking at iron and chromium into the respective ions that we need that we got from the solutions, I can see that chromium is the more reactive metal because when it goes in the reverse, it's going to have a bigger positive when it oxidizes. So it's better at losing electrons. Therefore, chromium is your anode. Okay, again, I got these from the reduction potentials. I just transcribed them. And therefore, iron is your cathode. Okay, now what do we have? We have the compound NaBr. It's also soluble because Na breaks apart to +1. And we have Br negative. It's very soluble because the charges aren't very high. All right, now, before I see where they move, iron, and then we have the what? Iron +2, chromium, and then chromium +3. Okay, electrons flow here, and at the cathode we're going to have reduction. We're going to have a buildup here, and this is going to give, this is going to eat up and get smaller. So a little piece of this gets smaller and makes the chromium +3. So who's going to move where? Well, we're going to have Na+ in this salt bridge moving to what? Replace the iron +2 that's actually getting reduced. Reduction occurs at the cathode, red cat. Okay, and we're going to have the Br negative move this way to counterbalance the increase of chromium +3 when it oxidizes. Okay, so that is our cell, and of course at standard condition, what is the concentration? It's going to be 1.0 molar along with 1 atmosphere pressure and 298 Kelvin, and it's a molar compound of what? Iron nitrate. It actually is iron 2 nitrate because it's +2. And this is also 1.0 molar, and this is going to be chromium 3 nitrate, not because of 3 nitrates, but because chromium is +3 in that example. Okay, and of course these are aqueous. Therefore, I really should draw, as I said before, the nitrate ions. Okay, so now we're ready to rock and roll. Oxidation half reaction. Okay, well, oxidation would be that the chromium becomes chromium +3 and 3 electrons. Put in as many electrons as you need to make both sides of a half reaction equal. Okay? And then we're going to have what? Iron +2 gaining 2 electrons to become iron 0. Reduction is gaining electrons. And let's put our charges. This is going to be a positive 0.14 going in the reverse. And iron +2 reducing as written because it is reduction, and I have it, it's going to be negative 0.44. Doesn't like to, does it? And I can see that I already made a mistake. This is positive, if you're screaming at me, 7.4. Okay, I was looking at, oh, I made a mistake. Now, the reduction potential as written is negative 0.44 volts. Now, some people will say, listen, Mr. Grodsky, this thing doesn't like to reduce. Why would it reduce? Chromium is so good at oxidizing. It's positive 7.4. It can overcome iron's poor reducing ability. Because when you add these guys together, okay, you're going to get, remember, it's a positive 0.74 plus a negative, so you're really kind of subtracting. So what you get, party people, is you're going to get positive 0.30. And you get, it's spontaneous. Now, you know it lost some of its power to use some of the energy to help this along, so the voltage isn't very high. Now, getting back to our overall net ion reaction, these reactions aren't really right. You notice I have 3 electrons and 2. That's not going to work. We have to balance our electrons overall. We know we're balanced in each half reaction, but to get the overall, we can't produce 3 electrons and accept 2. So what we do using the distributive property, I'm going to multiply by some number to get the same number of electrons. What's a common factor between 2 and 3? Very good, 6. So I multiply everything by 2. What do I do that? 2 times 3 gives me 6 electrons. I multiply 2 times 1, 2 times 1. And how do I get 6 electrons on this side? Right, multiply by 3. There's 1 of these, so 3 of these. 3 times 1, there's 1 of these, so 3 times 1 is 3. And then 3 times 2 is 6. And if you notice, we are now balanced. So we can get rid of our electrons. And now we put these guys together using the coefficients to Cr plus 3Fe. Don't forget the charge. And then you have 2 Cr plus 3 plus 3Fe0. And if we, as a good check, make sure both sides of the half reaction have the same charge. Well, this is a 0. It's a standalone, so 2 times 0 is 0. 3 times 2 is plus 6 on this side. 3 times 0 is 0, plus 2 times plus 3 is plus 6, and lo and behold, the charge, or we say in New England, the charge, is the same on both sides. We know we've done this right. It's a net ion reaction. We don't put in the nitrates because they're spectating. All right? So we've done almost everything. Almost done here. Okay? What would be the voltage? Would the voltage increase, decrease, remain unchanged if the saltbridge compound was changed to iron 2 chloride? Now, what's iron 2 mean? Iron is plus 2. That's what the Roman numeral tells me, because iron actually can become plus 3 as well, so it's telling me which one. Chloride means it's binary, it's just an element, and we know that chlorine is -1, it's a halogen. So you crisscross, or you figure it out that we're talking about a compound FeCl2. Okay, now the question is, if I put this in the saltbridge, is it soluble? I mean, so iron is plus 2, so maybe it's sticking together too strong. If you go to table foo-foo, you'll see that the halogens are actually very big ions because they gain an electron and therefore get bigger when they go. So this is soluble. If you look at table foo-foo or table F or solubility table, halides are soluble. There are some exceptions. Iron's not one of them. So this does break apart, okay, to 2 chloride ions. And these are aqueous. So what does this tell us? This tells us these are free ions. So let's put them in, see what we have here. So the Fe plus 2 would travel down. Oh, hold on. Okay. And it would, whoa, wait a minute. It would add to the iron plus 2 that's already there. Isn't iron chloride, iron chloride, and what was the compound? Iron nitrate that's in the beaker. Iron nitrate. Aren't these common ions? Yes. They both have what? Iron plus 2 in them. So by adding a common ion, the same charge, this guy's plus 2, so is this guy, I'm increasing the number of iron plus 2s. Now, what does the chloride ion do? The chloride ion is increasing too. The chloride ion is just like the bromide, would actually travel down and help counterbalance the increase in positive ions, but it would help on this side, but it wouldn't change the reaction because what? Chlorine ions are not in the reaction. Iron plus 2 is. So we have effectively increased the iron plus 2. You have to be able to see that. So no problems. What do we know? If we increase the iron plus 2 concentration, and brackets represents molarity, and that's our what? Stress. What's the response? To lower the Fe plus 2 concentration. And how do we lower it? Remember, this lowering is what the reaction does. We pushed it back up the hill. This is going to fly down the hill. The question is, which side? Is it going to favor the reactants or the product? So very simple. To get a lowered F2, I've got to either produce more of it going this way, since Fe plus 2 is a reactant, or I use it up. So if you can see, it's going to shift right. To lower Fe plus 2, I have to use it up, so it shifts to the right. And it makes the forward reaction even more spontaneous than it was to begin with. So this would also increase the voltage just like the first problem, but for a different reason. but they both shift the reaction to the right to make it more spontaneous. Last question, how would the molarities change in each half reaction based on the condition of step K? Well, this step K here shifted the reaction to the right. So if that's the case, aren't I going to increase chromium plus 3? Aren't I going to use up iron plus 2? Yeah. So what we would say is, even though these are initially at 1 molar, what would happen is the chromium, this concentration would go up. So you can just say the chromium plus 3 concentration would go up, and the Fe plus 2 concentration would do what? Would, of course, go down. That's what happens in that shift. And that's it. And that's your justification. It's good enough. So I hope you can see that we've got all of the compounds, all of the spontaneity, all of the talk here that we've been dealing with, and now Le Chatelier's principle, which is the change in spontaneity and the discussion of equilibrium in these problems. Hope that puts it all together for you, and you found that to be very doable. Good luck.